What's up, everybody? How's it going? It has been far too long since we've done a Google coding interview on this channel. It's been almost 4 months. This is uncharted territory, but fear not, this hiatus ends with this video. That's right, this is another Google coding interview, but this time conducted not with a software engineer at Google, but with a software engineer at Facebook. No ordinary Facebook software engineer, though. This is the one and only David, also known as Second Thread Online. He is a very good competitive programmer, and I know I have a thing for competitive programmers with these Google coding interviews. It's just so fun. I will try to do a Google coding interview with a non-competitive programmer in the future, but this one was just super good. David is a really nice guy, really smart guy. He is a grandmaster on code forces, and I gave him one of the hardest questions that we have on Aho-Expert as part of our coding interview assessments. By the way, if you're preparing for your coding interviews or your systems design interviews, do check out my company. Go to algoexpert.io, use the promo code CLEM, CLEM, for a discount on the platform. Aho-Expert has helped tons of software engineers land jobs at Google, Facebook, all sorts of tech companies. But going back to the Google coding interview, I conducted this one just as I conducted any interview when I worked at Google. That's 45 minutes on the clock using the most delightful coding editor out there, Google Docs. At the very end of the video, we did a little bit of a debrief, and with that, I hope that you enjoy the Google coding interview. Okay, David, so are you ready to start the interview?
I think I am, yeah, we'll see.
All right, great. So I'm going to press start on the 45-minute timer now, and let's begin. So if you were to take out your phone right now, either an iPhone or an Android phone, and you were to look at your keypad on your phone, you would likely see something like this. You would likely see something like this, where you've got the numbers, right, the digits, 1, 2, 3, all the way to 9. Okay. But you would see, like, on the digits, you would see letters, right? So, like, under the 2, you would likely see ABC. Under the 3, you would likely see DEF. And this is something that was, like, really common in old phones. They still have it in modern phones, but it was really common in old phones. And the reason it was common is because it allowed you to have phone numbers that kind of read like English. So I don't know if you've ever heard of the company, like 1-800-Flowers. I'll copy-paste it here, 1-800-Flowers. It's the name of a company, but it's also a phone number. And this phone number is actually, let me copy it here. This phone number is actually 1-800-356-9377, but it kind of maps to 1-800-Flowers. Does that make sense?
Yeah, that makes sense to me, I think.
Yeah. So the point that I'm trying to get across here is that if you've got a keypad like this with digits, numbers, phone numbers, can represent different words. I'll give you one more example. Like this phone number here can represent either Clement or Clemdot, okay? Or any other, like there are a bunch of other combinations of words. Now, I want you to write an algorithm or a function that is going to take 2 inputs. It's going to take a phone number, which is going to be a stringified phone number, as well as a list of words. Okay, so I'll give you a sample input right now. Sample input would be these 2 things. You've got a phone number and you've got a list of words. And I want your algorithm to determine which of the words in this list of words are contained in this phone numbers. Kind of like the word flowers here is contained in this phone number. And so for this particular input, you would return something like this, because these I'll put output here, because these words here happen to be in this phone number.
So I'm looking for ones that occur anywhere in the phone number, right?
Anywhere in the phone number.
Any substring, like any continuous range?
Yes, continuous is the key word there.
I see. Interesting. Okay, so I guess maybe first it might be helpful for me to do some simplifications.
Okay.
Of the problem a bit. So yeah, okay. So for these words, if we just want to see if some word corresponds to like some number, it's probably easier if I replace each letter with whatever number it would correspond to, right? So in the first instance, like 366 could be a bunch of things. But it might be easier, like if I'm looking for foo, for instance, foo would be, well, it would be 366. So instead of looking for these words, it might be easier for each word I have, so like for foo, I could turn it into like 366.
Yep.
Now I want to see, does 366 occur anywhere in the, like as any substring in this? So that might be helpful.
Okay.
And then I can do this for each word. So for each word in the order size of input, then I can look through each of those. Yeah, so on one hand, it seems like maybe it's possible to do some Aho-Corasick sort of thing here, but that might be a bit unnecessary. I guess for like one question that I'm going to ask is the phone number any specific length? Is the phone number, might it be like really, really long, or can I assume the phone number is just like the length of a normal phone number, like 7 digits or something?
You can say that the phone number can be of any length, so it's effectively like any contiguous or continuous amount of digits. But don't worry too much about the fact that it might be past some gigantic number. So I guess my point is, it's not necessarily 7 numbers. It could be, like 15 numbers or something like that.
Sure.
But don't worry about too large of inputs.
So, like one solution path that I can go down would be something where the final runtime would be order phone number length squared. That would be one solution path that I might be able to use. And the idea behind that would be I can find some representation for every continuous range of this phone number. So if you consider every start point and every end point of the phone number, you'll have some big value. But what I can think about is like I can compress that value into some other value where if some word is also equal to that value, there's a very good chance those are the same. And that's a thing called string hashing. So I guess I'll get there if this would be a solution that would be helpful. But I spelled length wrong. GTH. There you go. So yeah, so that's one thing that I could try. Another thing might be if all of my words are short, if I know all of my words are like some relatively small length, then I can only look at the substrings that are of that length. So if I know maybe all of the words aren't super long, then I can check only substrings of that length. So that would be order like number of different word lengths times the length of the phone number.
So let's assume that for the words, they are of any length between 1, so they can't be empty, between 1 and the length of the phone number.
Okay, so yeah, so that's a good thing to keep in mind. So I guess that means this solution wouldn't be very helpful at all because it would pretty much just be the same as this top solution. All right, so then, yeah, I guess it might be interesting to consider what if we tried some Aho-Corasick here. So basically, we can imagine, let's say I have some trie, basically, and the trie consists of all of these words.
Okay.
Then what I want to find out, basically, is for like for each prefix, I want to see for some suffix of that prefix, what's like the longest suffix that exists as some path in the trie.
Okay.
And then that'll have like a link back to, well, the details I guess are a little complicated, but we'll be able to see like where this goes in the trie. And then based on like where that goes, we can take several steps up and like repeatedly look at that. And then we can mark all of the different words that we see there. So yeah, so I guess basically the idea is like one thing that I might consider for the solution path is maybe I'll build some trie of all of the words. And then after that, I'll have like some links for each node in the trie. Or I guess there are only 10 digits, right? So I won't have 26 links, I'll have 10 links. For like which trie node you reach after each step, or after like reading every next possible input.
And I guess, David, just to cut you off here, when you say you're going to have a trie of all the words, will you be putting the words in the trie as strings, so this current format, or as digit strings?
I'll do it as digit strings. So basically, I'll convert all of these words into digit strings, and then at the end, in order to validate some... Yeah. At the end, I'll have just like a bunch of digit strings, and then at the end, I can just say, if some word matches, I can just check, does that digit string match as well?
Gotcha. Okay.
Yeah, okay. So maybe it might be helpful for me to draw an example for myself, just to kind of remind, because it's been a while since I've coded Aho-Corasick myself.
Okay.
That's for
By the way, I'm not sure what that is.
What it is.
So
okay.
if you want to just explain to me what the Aho-Corasick is.
Yeah. Okay.
Because I understand what you said with the trie, but I'm not sure what that like word is or name for something is.
Okay. Yeah. So like well, I can explain the general idea. I can definitely, so like if the solution path you're looking for is n squared, I can definitely go down the n squared route. The thing with that is that route is completely different from the linear time route that I would be considering here. So like going down that route, I guess might be helpful if that's what you're looking for. But if you're looking for something linear, that like this is completely unrelated. But the idea for Aho-Corasick is that you've got like some trie. So maybe let's have some words. Maybe we have like bat. We have the word at. Maybe we have ATT, or like AAT, for instance. So
sure.
The trie for that would look like you have an A, then you have a T, but you also have, it's kind of confusing because these are like the letters I'm drawing are really the edges. So you've got like, this is a node here.
Yep.
And then, yeah, I'm sure you know what I mean by this, but
yeah, this is just helpful to just visualize it. Okay. Yep.
Sure. Yeah. Okay, so this is the ATT. I'll bold this. I guess I'll bold and underline it because that means that's the end of some node. This is also the end of some other node. And then that adds these two words. We also have AAT. So in code, these would be ordered, but just for simplicity, I will make them unordered.
Sure.
And this is T.
Okay.
Here. And then we also have bat. All right,
gotcha.
So this is kind of what the trie would look like. Now, the idea with Aho-Corasick is when we have some of these, like if we have some big string, okay, so I guess this example is with letters, but the real example will be with digits instead of letters, but I guess it's not too different.
Yeah, that's fine.
So if we're looking through some string that looks like this maybe, I guess maybe, yeah, let's say we're looking through that string. Then the idea is we're going to consider every possible prefix. So we'll consider the prefix A, then we'll consider the prefix AT, then we'll consider ATB, and we'll keep going from there.
Yep.
And for each prefix, we want as much as possible of that prefix to be, sorry, there's a motorcycle outside my window, to be in this trie as possible.
Yep.
So in this case, let's say we're looking at just AT as the second prefix. We can follow that down the trie and we'll get to this A and then we get to this T.
Yep.
So that would be a prefix of length 2. Then when we see this following B, we can't actually take a B from this T.
Yep.
So we need to follow whatever the failure link is from this T to the next thing that has a B. So in this case, if we try going up, or we'll try looking at the suffix like TB. And if TB exists somewhere in this trie, then we'll follow the TB. In this case, we don't have a TB. We can't do TB. So we just have to look at just the B. So we try just the B from the original, and we get to just this node. So then after reading the B, we would be at this node here.
Right.
Then we would try to read the A. Since we were at this node, we follow the A link, and now we get here. So now we're here after reading the A. Then we read this T, and we go to this node here. So the idea is that for each node in this trie, we want to say, if we can't reach one of the nodes that we're looking for, we want to see, we're going to go back up to some other node. And then we want to see if we go up to this node, like how far do we have to go up so that we're at some suffix of ourself? Like what is the early, like the best thing in the trie that's some suffix of this? In this case, we have ATT. We want something that would be a suffix of it. It would be TT. So that doesn't really exist in the graph. Let me look at a better example. So if we're at BAT, if we read in this BAT and then we read another T.
Yep.
Then when we do this, first after we read the BAT, we'd be here. Then when we read the second T, we'd be like, okay, well, there isn't actually an outgoing edge labeled T here. So we have to find the last time that exists. Yeah. We have to find like the earliest fail link for this. So this would be the suffix AT. And AT does exist in the trie. It's this one here.
Gotcha.
So we would jump to this, and now we're like, okay, but now we can take the T link. So you'd take this link here, and then you'd end up at this node. That basically tells you if you take a bunch of steps, you want to know like which trie nodes do you hit, basically.
Interesting. And so this is how you are able to kind of optimally, like, because with your example of BATT, when you get to this T here, and like you said, you don't see the second T, the fact that you're somehow able to jump back to this AT up here, and then you get to the ATT, this is sort of like the optimal aspect.
You just kind of broke up for a bit.
Oh, sorry, can you hear me?
I can now, yeah.
Yeah,
like,
so
until you said jump back was the last thing I heard.
Yeah, so I was just saying, like, the fact that you can quickly jump back to this AT up here is what allows, like, the optimal aspect of what you're describing, right?
Yeah, that allows, in order 1, I can figure out if I'm at this node and I read a T, which node will I be at in the next step.
Gotcha. Okay, yep.
So the idea is there's a really common algorithm that can, or I guess it's not common, but there exists an algorithm to build this thing. Basically, you build a trie, and then on top of building the trie, you do something else. And to be honest, I don't totally remember that, so we'll have to figure that out live, and that'll be, I guess, fun to watch me do. But in addition to that, once you have this thing built, then we can find all of the nodes that we visit in the trie across reading the entire phone number.
Right.
So we'll read the entire phone number. We have all of these nodes in the trie. Then we can do like a BFS from all of these nodes in the trie to figure out which nodes are actually reachable. And for each one of these nodes, you can follow the node or the failure link for that node. Those are all fine.
Okay.
And then, so now we have all of the nodes in the trie that are reachable across any substring of this phone number. And now for each of these words, we can just say, all right, the word corresponds to some node in the trie. Was that reachable or not? So that'll just give us our answer.
So do you mind, David, writing out just very briefly, like, I don't know, maybe a bulleted list or something of the steps that you're going to go through from start to finish?
Sure, yeah, that's a good idea for sure. It's probably helpful for me as well. Okay. Oh, I don't want it there. So it's right under the output section. Yeah.
Yep.
So the first thing I'm going to do is build the trie. Then as I build the trie, I guess this needs to be at the same time, if I remember Aho-Corasick correctly, I need to calculate the failure links for each node in the trie. So these two need to kind of happen in the same path, I think. Or maybe not. Maybe this is just second. Yeah, I'll just do this 1 second. So then once I have this trie, then I'm going to walk through the phone number, keeping track of which node in this trie I'm at each position. Like at each digit in the phone number.
Okay.
So that'll just use the failure links to find the next one in constant time. And then finally, once I have that, like this will tell me which nodes are reachable, like which nodes in the trie are reachable. And then I want to do a BFS on the like directed graph of the failure tree. So now I want to do a BFS from all nodes that I was at, like in step 3.
Yep.
Along the failure edges. And by doing that, once I've looked through all of these, as I do this BFS along failure edges, then I can see this will tell me all nodes, all trie nodes that are some substring of the phone number.
Gotcha.
And then like once I have that, then I can just iterate through each word, I guess, and then check if it was visitable, and then just print out the answer there.
Okay. And just one quick question. So this thing that you keep calling Aho-Corasick, is that the algorithm to build the tree, or is that
that is the part that does this part right here? It calculates the failure links and then where you go after each step. So
Gotcha.
Usually I wouldn't write this myself because like I don't have it memorized because it's just like a thing on paper. So
Right.
like I would always just reference that. But yeah, that would do this part for me. It's like, oops, it was like a research paper that maybe people named Aho and Corasick invented.
Gotcha. Okay.
So yeah, so that's what this part does. But once I have that part, then the rest of it is all pretty straightforward. So Aho-Corasick just does this part to answer your question, yeah.
Understood. And so, for the sake of this interview, though, how about we do this? Let's skip this part for a second. Like, let's skip the part that you just said, is going to be difficult for you to re-implement. Let's assume that we have that at that point, and you can tell me, whatever the structure looks like, and you can just implement this part.
Sure. Okay, sounds good. Yeah. So I'll just like I guess write a blank method for it. And then
Sure.
if this were like a coding contest or like a real job, then I would look it up and just paste that part in this method, if that
Okay.
works.
Yep.
So yeah. So is it all right if I start coding then?
Go ahead.
Sounds good. So like this would all be inside some class, but I won't actually write the class because it'll kind of use up my indentation space. So I'll just start with like
fine.
some main method, and then I'm going to be using Java if that's all right.
Totally fine.
So like that's my main method. Actually, maybe is it all right if I just write a method that takes in this as input, like you mentioned, this phone number and this words array?
Yeah, in other words, it can be as simple as possible as far as like the function signature. You don't need to like read
Sure.
from standard input or something.
So you're gonna give me this phone number, and then you're also gonna give me an array of all of the words that are interesting. So the first thing I'll do will be static void toNumber, I guess static int toNumber. And then we'll call this phone number letters. And then I'll make int array phone number equals new int array. So then I'll convert all of these to like a more reasonable format, I guess.
I choked.
So now they're just indexed 0 through 9 instead of the characters 0 through 9. So then toNumber, this will like convert the like some character array into a number array. So array word, and then some int array to numbers. So then, yeah, I guess let's see. Is there an easier way to do this? They don't all have 3 letters, which is kind of annoying. It would be nice if I could do some math there, but it might be easier to just like hard code some array for what works here. I guess these words are all going to be lowercase, right?
Yeah, let's assume that everything is lowercase, and for simplicity here, if you can just write like the first letter mapping or whatever you're describing, but you don't have to write all of them, because I understand what you're saying.
Sure, yeah. So so it would be something like this. So A, B, and C are all 2. The next 3 are all 3, etc. So that would be like, it shows like for some character, what does it map to? The character is starting at A. And then the rest of the method would just look like this. Or minus letter A. So now from this, we can turn some word into the phone number digits that it would represent.
Yep.
Does that all make sense?
Yes, and just to confirm, the phone numbers, or the 2 number gives you a list of integers, you said?
Yeah, so if you pass in, I think foo would go to 366, like we talked about earlier. So this array would go to 366 as an array.
As an array, okay, yeah. Okay.
Awesome. Okay, so now I'm gonna make an array of integers here because I think that might be easier to handle. So it'll be word letters dot length by something. To number of word letters I. So this just converts each of these into numbers. So now I'm dealing with things 0 through 9. That's a little bit easier. Okay, so now this is like the Aho part, I guess. So well, I guess yeah. Let's just, I'll write out the general structure for how this Aho thing works, and then I'll worry about the actual algorithm in a minute. But we'll make a trie node maybe. I'll just call it node for a trie node. And then this is going to have some node array of like kids in the trie. So this is going to be some new node array of size 10, because there are 10 different, our alphabet is of size 10.
Okay.
And then it's also going to have some node, like a failure link. And this would be calculated by Aho. And then it's also going to have a node array like repeat fail, or like next with fail. And this is also calculated by Aho. And this is an array, actually, not a single node. So what this does is, this is like if we read some letter A, like I mentioned in this example up here, if you have bat and then you read a T, it'll say, okay, which node do you go to after reading the T? So in this case, you would go to this node in the bottom left.
Yeah.
So this is what this fail thing does. Okay, so I'll have this add word signature here. This will have some int array word and then which index I'm at. And now we want to build this trie here. So we'll have a trie equals new node, and for int array for each array in words. Then we want to add that to our trie. The word and the index will be 0. I'll talk about how we build this into the kids, I guess, because that's pretty simple. So if index is equal to word.length, then we return. Yeah, that's fine. And then I'll also have this return a node, maybe, because that might be helpful.
Okay.
Just for later on. And then otherwise, so we know which kid we want to go to. So int kid will be the word at this index. This is what character of the word we're about to add to the trie. So now if kids at this kid is equal to null, then kids at this kid will be a new node. And then we want to return, this would just return this node here. But then otherwise we would return kids at kid dot add word, the same word, and then the index plus 1. Like go to the next character in that. So this will build our trie for us, basically. So, okay, so now where was I? So we add each of these. We also, it's probably helpful, instead of doing a for each loop here, I probably want to do a regular for loop to make looking up the answers more easy. So we'll also make a, node array, like end at equals new node array words.length. So now I can store for each word which node in the trie that word corresponds to. Since this part is just linear, then this whole thing runs in order size of input. So order total number of characters in the words.
Okay.
So now, like at this point, I would want to build the Aho. So we'll worry about that in a minute if we have time. Then after that, I want to go through the phone number. So for int I in phone number. We want to worry with that. We also want to store which node we're at. So this is like, it starts at the trie node, the root of the trie. After each step, we will take this next with fail link to see which node we are after reading the next character. So at will be at dot next with fail at just this index. We also want to mark all of these as visited. Well, I guess all, all false. So now we'll say at dot visited equals true up here. And then also in this case, after we visit a new node, at dot visited equals true. So we know all of the nodes that are visited here. Now I want to do a BFS. So this is the BFS part. First I need to get all of my nodes that are visited here. So I'll have a DFS method to add stuff to some queue. So in C++, you could just use a queue. It would look like this, queue of node. I think you said earlier that you don't usually code in Java, but the Java equivalent of this is called an array deck.
Okay. A DQ, yeah.
Yeah. So it's like a double-ended queue. I'm only going to use it as a normal queue, but this is like the fastest equivalent for it. So this is what people usually use.
Okay, yeah.
So this is the BFS list. So now for node kid in nodes, if this kid is not equal to null, then bfs.add last this kid. Or I guess we'll just DFS from it, right? So DFS from kid.dfs, pass in the same queue. And then finally, if I'm visited, so if visited, then bfs.add last add me. So add this. Okay, very cool. So now I need to add these all to this queue. So this is array deck of nodes, which I'm calling BFS. And now I want to say the root of the trie, which is just trie.dfs, pass in this list. This will fill up all of the start nodes for my BFS. So now any node here is one of the nodes that we were at when we were looking through the phone number to see which node in the trie we were at.
Okay.
So that's like what's going on so far. Now finally I just need to do this BFS. So while not bfs.isEmpty, node next will be bfs.remove first. If next.failLink is not equal to null, and next.failLink.visited, or if it's not visited, then next.failLink.visited equals true, and then add that to our BFS. Okay, so this will now mark all recursive like suffixes. So in this case, if the string were just if the phone number were just like the equivalent of the word bat, then we would have this. But in addition to marking you can see B, you can see BA, you can see T, I need to recursively say, okay, you can also see AT, and then you could also see just T as well.
Sure.
So that's what this BFS is doing.
Yep.
All right. Awesome. So now finally I just need to return this answer. So what did I say this wanted to return? I'll say we'll return an array list of, do you want me to return like the indices or the actual words? I can do either. They're about the same difficulty for me.
Let's return the words, and in no particular order.
Sounds good. I'll just do the same order as input, if that's all right.
Sure.
So now for each of these, what did I call this? For each of these endat nodes, I just need to see, okay, each of these words corresponds to some place in the trie. I just want to see whatever this corresponds to, was that something I was able to visit in my BFS? So for int I equals 0, I is less than end at dot length, plus plus. And then we'll have this array list of strings to return in the array list, and return that. So yeah, okay. So if end at I dot visited, that means this occurs as some substring of the target string. So then what I want to do is add this to the list of things that I can visit. And this will be word letters. And then I just return that at the end. Okay, very cool. So yeah, so there's one part that I'm still missing here, I guess, and that's this build Aho part. So this is the black box that I've left. Would it be maybe a good idea for me to just walk through this whole thing for you first, or should I start working on like reinventing the wheel here?
Yeah, let's start by having you walk me through the entire algorithm, and you can see if you feel like confident in it, and also if you can walk me through the overall time complexity and space complexity, I suppose, by going through it all.
Sure. Yeah. So okay. So here's like I'll kind of separate this with some comments on what's going on here. So this first part is just like use a format that I'm comfortable with, which is just all numbers. That way I can index things without having a bunch of empty space. So this is just like make it more comfortable. All this does is use numbers instead of letters everywhere. So the great part about this instead of an IDE is we do get spell check.
You do get spell
check. If there's one upside to coding in Google Docs, that's it. Yeah.
What, so you're saying Google Docs isn't delightful otherwise?
I mean, if it had a dark theme, maybe they'd change my mind. You just gotta have that. All right. So anyway, yeah. So for this part, this is just like build the trie. And then the Aho-Corasick just runs on top of this trie. Okay. So I guess let's walk into this add word method. So I'm gonna scroll down to that and then talk about that.
Yep.
So the add word, this is just like kind of classic college level intro to data structures, build a trie. So the idea is we're going to pass in this array. In C++, this is like passed by reference. So in C++, it's equivalent to that. In Java, this doesn't copy the whole thing. It just passes a reference to it. So this is like order one calling this method.
Yep.
But anyway, yeah. So if this means if we're at the end of some word, then we just return this node. So this will return whatever trie node corresponds to this word, assuming we've already processed index number of letters in it.
Okay.
Then we want to look at which kid we should go to from this node. So that'll be this part right here. And then if that kid is null, that means we haven't seen, so like let's say we're at like AT or whatever, we haven't seen another T yet. So we need to make a new trie node for that so we don't have a null pointer exception. That's just what this does.
Yep.
And then we just recursively ask our kid, well, for the rest of the word, what would we be at? So since the rest of the method works, that part will work as well because we have our base case here.
Sure.
So yeah, so that's how we build the trie. Then we would run Aho, which I'm pretty sure we can do just with BFS going down the trie. But yeah, so anyway, but then just moving on from that.
Sorry, David, but just to cut you off, can you add also the like time complexity of each of these parts?
Sure, yeah, for sure. So this part here, this is like order sum of sizes, sum of word sizes.
Yeah. So like the total number of characters in the entire words array is what you're saying?
Yeah, exactly.
Okay.
And it's both that size and space complexity, worst case.
Yes.
And then, yeah, what else is this? So this Aho is the same thing. So it's order sum of word lengths as well.
So Aho runs
size.
It runs in linear time.
Yeah. It's just a BFS. Yeah.
Yep.
It's just a clever BFS. And then this part, what am I doing here? Oh, okay. Yeah, this is just like we mark, like we literally just traverse through this thing. So it might be more helpful to put this here. This is like we just walk through the phone number part. So this part here will just be order length of phone number for that much time, and then order one space. But I guess we're already storing the phone number here, so we're not gonna beat order length of phone number space anyway, like in the grand scheme of things. But I guess it's not too important.
Yeah.
So what this does is just Aho will give us, if we fail for each letter, where do we go to? And that's calculated in this, oh, I've done something. That's calculated in this part here, if I were to write that method. So we can just walk through the trie for each next step, saying what character do we go to? And then we mark all of those as visited, saying like, you can get here from some prefix of the characters. And then by doing this BFS right after, we want to say, for the rest of the characters that are some suffix of each of these trie nodes that are visitable, which ones of those can you hit?
Right.
So then this BFS here, it's just a normal BFS. So since the total number of nodes is the total length of the sum, like the sum of the word lengths, then this BFS will run in that time because the number of edges is just the same as the number of nodes, because the number of edges is a tree basically.
Yep.
So this part is also order sum of word lengths. Okay, very cool. And then, yeah, finally at the end, we just iterate through. So we stored for each word that we're considering, which trie node does this correspond to? So I just iterate through each of those and say, okay, if this node was something that's a suffix of one of the trie nodes we were at while iterating through the phone number, that means you can make it by some suffix. So I add it here.
Right.
And yeah, that's the idea behind it. This DFS just like looks through all nodes, so that's not really worth covering, I don't think.
Yep. And
so I'm pretty confident in the general idea. It might not compile. I might be missing a semicolon or something, but that would be pretty easy to fix if I had if I were able to compile it.
Yep, exactly. Yeah, and I don't think we need to check that right now. I think we could check that if we wanted to, but I don't think it's super important here. And so overall, the total complexity of this algorithm is.
Oh, sure, yeah, I should definitely cover that. So overall, it's order length of phone number plus sum of word lengths. That size and space. Now, if you don't count the space of the phone number letters, so if you don't count the space of this array, then it would just be this much this much time, and the memory would just be, so it'd be this much time. The space would just be the sum of word lengths for the space. Oh, I guess that's not true. No, because I make an array somewhere, so it's both this time and space.
Okay.
Just kidding. Like the reason it uses that much space is because I make this end at array. Wait a minute. Hang on. Give me like 10 seconds here, and then I can get you an answer for sure.
Take your time.
Yeah. So it's not. It's actually the space complexity is order sum of word lengths. And this is just the time.
And you're still there, right?
I am, yeah.
Yeah. And so the reason it's some of the word lengths, especially with regards to the tree, is because in the tree or in the trie, effectively, like, you have each word at most once, and even some characters are repeated. Like, some characters will be kind of like duplicated. Okay.
Yeah, so it's probably going to be a little bit less, but like worst case, it might be you might have every character or almost every character.
Right. Okay. And then of course we have also like the digit phone numbers and all that, but those are all either the same or less than that.
Yeah.
Okay.
I suppose, this might make it linear on the phone number length as well. But that's kind of like small details, I guess, that aren't too relevant.
Oh, yes. If you're creating also the phone number, if you're storing that as an additional thing. But yes, okay.
So, yeah.
Okay, great.
Awesome. Thank you for the interview. I appreciate it. It was a fun problem for sure.
At this point, I think we're done. Thanks so much, David. This is like right on time. We've got 1 minute left. So maybe now we can do like a quick debrief. So maybe like, why don't you start by telling me and the audience, like, what did you think about the problem and how do you think you did and all that?
Well, it was a really good problem. I really enjoyed the problem. It was super cool. I guess it would have been helpful if I had like coded this recently, because it would be easier to like not have to, I guess, black box it when I'm explaining how it works. It would be easier to just not say this is like a well-known thing and instead just explain it like for the first time. But yeah, so I guess like this is the main thing that I wish that I had done better, this having this black box here.
Right.
But beside that, I think, I don't know, I feel like I was pretty comfortable for most of it, and I think it went pretty well, I guess. I don't think it's possible to do better than this runtime if you're doing everything on a single processor. I think this is the best you can possibly do. So I don't think there's like a better solution out there that I'm missing. Maybe, I don't know, I'd love to hear, is there just a simpler way of doing this that I just didn't see?
No, so I guess like if you want, I'll give you like my thoughts. So I think you did super well from an algorithmic point of view. I think you did, really fantastic. And I really want to emphasize this to the viewers. Like, the solution that David covered is not the solution that I personally would expect in an interview. I went with it like at the very beginning. You even asked me. You were like, do we care about this solution or do we care about the like n squared solution or whatever at the top? Like if you scroll up, you had written a different solution path, David. And in an interview, I would not expect someone to go through this with the like Aho algorithm and all that. And I was expecting more of a, you can build kind of a what's the word, like a simpler version of a suffix tree kind of structure that would run in n squared time. With respect to the length of the phone number, for example, if you dump every suffix in the phone number in that tree, and that would be like acceptable in a coding interview. But David like knew about something even fancier and even better, went with it. I think it was great. I think it was better to not have you write out the Aho algorithm because like at that point, like I trust that you are familiar with that and that you kind of know how it works. And I've gotten enough signal from your algorithm skills. I don't need you to jump into that and to try to reinvent the wheel, like you said. And you would probably just use that from like a library or something if you really needed it on the job. And then you were communicating really well. I didn't lose track of you at any point. The one like super tiny nit that I will give you, David, if you want, is just like here with the BFS. I got a tiny bit confused because you named.
Here's my Aho code, by the way. But yeah, anyway, sorry, what were you saying about the BFS?
Yeah, I was just saying that you named the the queue BFS, which I found a tiny bit confusing because like you used DFS as a verb, but here BFS effectively as like a noun of the queue.
Is the name of my queue. Yeah. Maybe I could have done a better job there for sure.
But I mean that's like a nit, and I ended up following you. But you see like here like tree.dfs passing in BFS like reads a little bit like
a bit confusing, yeah.
Yeah, but apart from that, like great job. Like I said, all the rest of the code was great, and your communication is like fantastic. You walked me through everything, totally understood. Like, and again, like I got to commend you for being able to explain something that is a complex algorithm with an even more complex solution than maybe the expected one to someone who might not be familiar with the way the algorithm runs and everything on Google Doc. So great job.
Well, thank you. I appreciate it, and it was a fun interview for sure. I enjoyed the experience.
Awesome. Well, maybe if anybody's curious, they can go check out. They can go look up Aho. Maybe I'll put a link in the description below to that. Thanks again so much to David for for being down to do this interview. Go check out his channel. I'll put the link to it in the description and in the comments below. He's got a great channel, great guy, great competitive programmer, and thanks a lot for doing this, David.
Yeah, thanks for having me.
If you made it this far, don't forget to smash the like button, subscribe to the channel if you haven't already, and I'll see you in the next video.